Hi, my name's Ann Witt, and I'm a geohazards geologist with the Virginia Department of Mines, Minerals, and Energy, Division of Geology and Mineral Resources. And that's just a really long way of saying the Virginia Geological Survey. As part of the work that I do, I study earthquakes, karst, and especially landslides. Landslides are my specialty. And in every part of the work that I do, I use LIDAR. LIDAR is a remote sensing tool that shows the surface of the earth in incredible focus. We can see things that we could not see before. And LIDAR has only recently become available within about the past 4 years for Virginia. We now have complete coverage in Virginia, and we're now able to see things geologically that we've never been able to see before. And that's really what the talk that you're about to see is about. I call it laser vision because we're able to laser focus in on things we never would be able to see. It's almost like putting on glasses for the first time. Everything was fuzzy before, now everything is clear. So I hope you're going to enjoy this presentation. I think you'll learn a lot. Thanks.
Hi, this is Ann Witt with the Virginia Department of Mines, Minerals, and Energy. And today I want to talk to you about using a remote sensing technique called LIDAR to look at Nelson County's geology and look at some varied examples of that geology. So let's go ahead and get started. So I want you to imagine if you were to strip the forest of all of its vegetation, what would you see? I'm a geologist, so while I love walking around in the forest and the bushes, they tend to get in the way of the geology. So it's really helpful if I can see the geology with all that vegetation out of the way. So here is an example of aerial photography from Google Earth. You can see US 23 running at the bottom, and this is near Big Stone Gap. So this is a mountain range. And let's strip all of this aerial photography away. You can't really see a lot of anything. Now we have the LIDAR, and from the LIDAR we can see the stratigraphy, we can see all these different layers in the rocks. All of these are sedimentary layers in through here. Some of them are made of a harder material like sandstone, some of them are shale, and they're eroding differently, and then they're eroding down into these debris fans down into the valley. So the LIDAR really helps us show the geology much better. So this is about 1,000 feet of exposure, of just exposed rock. All right, now this is another image from Google Earth, and for the most part in Virginia we have a lot of vegetation. You can't see a whole heck of a lot of anything. So let's strip off this vegetation and look at the LIDAR. Now we're getting somewhere. So this is a debris slide, a landslide, and you can see a lot of different features in the LIDAR with this one. This is about 1,700 feet across. You can see the landslide Headscarp up at the top. So this is where it's separating away from the surface of the earth and sliding down. You can even see horizontal cracks that are within the landslide body itself. Here's the toe down there, and it's actually, the landslide is moving over even older landslide material. So we know that this is activated at least twice, and it's reactivated more recently. And that's really the power of LIDAR, to be able to see things that we really couldn't see before. So I've been talking a lot about LIDAR, but what exactly is LIDAR? LIDAR stands for Light Detection and Ranging, so LIDAR. It's a remote sensing technique, and it uses lasers to basically sample the surface of the earth. Those lasers go toward the ground at a particular speed, and it's a known speed. So if you know when the laser leaves the airplane, goes down to the earth, bounces back up, and goes back up to the sensor, then you can start to calculate the distance from the plane to the earth. And you can also get an X and Y position using GPS. So there's a lot of different types of LIDAR: topographic, bathymetric, which measures the surface underneath the water, and there's also terrestrial LIDAR. So you can have LIDAR that's on the back of a van, or someone actually standing there with a unit and having a LIDAR sensor to capture different images. What we're going to be talking about today is topographic LIDAR, so flown from a plane. So a LIDAR laser returns thousands and thousands and millions of pulses that then reflect back objects that are on the ground surface. Usually these pulses are called returns, and one pulse can reflect back 5 different times. The first return that you have is usually the treetops or bushes or some sort of vegetation. What I'm most interested in, though, is the last return, the bare earth. So all of that vegetation is gone away. Now, some people who use LIDAR, like foresters, are interested in vegetation, and you can see that depending upon the LIDAR return. So what you get is a point cloud of millions and millions and millions of points. All those points then can be converted to a map of the Earth's surface. But each one of those points has to first be classified, and a lot of the different contractors that do LIDAR have an algorithm that processes those returns based upon their distance from the Earth and what they're hitting into different point classes. So over here on the right, you're seeing some of those point classes. A raw LIDAR point cloud is what's called a LAS file, L-A-S, okay? If it's a zipped LAS file, it's an LAZ file. What I'm interested in is this stuff, number 2 returns, ground returns. But you can see in this image, all of these different features at this airport, these are all points, millions of points, and each one of them has been classified based upon the return that they're getting. So once you then process those points into a surface, you get something called a digital elevation model of the bare earth. This is Central Virginia, and this gives you an idea of what you can get from all those millions of points. We can also then process them further into several different LIDAR products that I use on a regular basis. The basic one, as I was mentioning before, was the digital elevation model, but you can then take the digital elevation model and generate contours. So if you want to generate 10-meter contours, 20-meter contours, you can do that with LIDAR. The next thing that I tend to use a lot of are things called hillshades or shaded relief maps, and that basically shows the topography with a known sun angle, and the default is usually from the northwest, so it shows shading of the elevation that then shows the topography. I also use quite a bit slope maps. So in this case, the slope, the lighter colors are steep slope and the darker colors are less steep. If you then invert those colors, you can create something that's called a slope shade map, and I'll show you several examples of that later on. And then sometimes, I would say least often, I would use an aspect map, which shows difference in slope direction. So what I tend to use LIDAR for is to show the geomorphology of the Earth's surface. And today we're going to be looking at a lot of different examples of how geomorphology affects the Earth's surface. Landslides, floods, erosion, and especially humans all leave their mark on the landscape, and those tend to be hidden by vegetation, but they really can't hide from LIDAR. So in this case, we have on the right, this is Nelson County. Hopefully everyone's familiar with that. This is the 2018 aerophotography, and you really can't see the topography very well unless you're over here in the mountainous area. But once I strip all of that off, suddenly the topography from LIDAR is revealed, and we can see a lot of different things. And we're going to walk through this, and I'm going to take you through some of these interesting things that we can see. So today we're going to talk about geology. We're going to talk about the erosional patterns and features in geological bedding and contacts that you can see from the LIDAR and compare them to the geological mapping that's already been done. We're going to look at some human activity, specifically in this case mining. There's a lot of different things I could walk you through, but I thought we'd stick in the geology time frame and look at mining, look at quarries and pits, and look at adits. Adits are mine openings that are horizontal into the Earth's surface. We're going to be looking at rivers, looking at different drainage patterns, different meanders, scarrings, and cutoffs, and especially flooding. And what is near and dear to my heart is we're going to be talking about geohazards. We're going to specifically be talking about landslides, Hurricane Camille landslides, and looking at some of the new features that I'm finding that these are brand new within the past year on a project that I've been working on. So I'm really excited to show you some of these examples. All right, so let's start with the geology. Now, don't be intimidated by this. This is the 1993 geologic map of Virginia, and I've just clipped it out for Nelson County. Each one of these colors represents a different geologic unit at the Earth's surface. So someone has mapped these geologic units at the Earth's surface. So I'm going to walk you through really simply the geology that is in Nelson County. All right, so most, if not all, of the rocks in Nelson County are metamorphic rocks, rocks that have been deformed by pressure and heat over geologic time. And they are very old rocks. We're talking up to 1 billion years old. Over here in the western part of the county, there are slightly deformed rocks, metamorphic rocks, and we also have metabasalt rocks. So a basalt is just a dark colored volcanic rock. Think like Hawaii, those kind of rocks, except they have all been metamorphosed. So they have been deformed over time. Separating these two sets of metamorphic rocks, we have a fault zone. Now this is a really old fault zone, very old. And all the rocks that are in this area are very deformed. They've been deformed ductily, so they have kind of spread out and stretched as they have been deformed. Over here in the east, we have metasediments. So those are rocks that were formerly sedimentary rocks that have then been metamorphosed. And then there is also a narrow band here of metabasalt over here. All right, so that's what you really need to know about the basic geology of Nelson County. So Nelson County used to be an anticline, okay? So that is just a folded set of rocks. So a anticline, syncline is going to be something like this that dips down. And what has happened to that anticline is it has been folded during collisional events as the Blue Ridge Mountains were formed, and then also there's been low angle faulting. So this area has gone through a lot of different geological events to get to the rocks that we see today. So if we take a cross section from A to A over here and A to A on this cross section, this is what it would look like underneath the surface of the Earth. You have this low angle thrust fault here labeled the Blue Ridge Fault, and you have what used to be the anticline up here at the top that has eroded away, and we're basically seeing the core of this anticline. The oldest rocks in this area are labeled here as the basement complex. So that's that middle area in the middle of the county here. So those are where our oldest rocks are. You can see this high strain zone, that's the fault zone. Those are an area where there was a lot of strain on the rocks and they've been stretched out and deformed ductily. On either side, we have the Catoctin Formation. So that is that green unit that's over here. That's the metabasalt, okay? So there is a west limb over here and a eastern limb over here. So think of it, the anticline used to continue over this entire thing, and over geologic time, it has worn away and we're just seeing the middle of it. This is pretty much the geology of Nelson County. All right, so let's go back to our geologic map. Lots of different varied rock types, all sort of the same rock type, but different types of minerals. That really determines what the topography is going to look like. So if we strip off the geologic map and just look at the LIDAR, this is a DEM of Nelson County, you'll notice a few things. There's a couple of things I really want you to look at here. You'll notice that these high relief areas are very rugged over here. You have some high relief areas in the middle of the county. And then what's really amazing is over here in the metasediments, you can really see the structure, the grain of the rocks. And that is not by accident. Almost all the rocks in the Blue Ridge tend to have this northeast-southwest direction to them. And that's all dependent upon the underlying geology. Now you'll also notice what's really interesting. If you start to look really hard, and frankly if you start to look really hard at any LIDAR data set, you'll start to see really interesting things. You'll start to see features that cut sometimes across at oblique angles. Here's one right here cutting across, one right here that's in a drainage cutting across. We call those geologic lineaments, and basically those are straight line fractures, joints, sometimes they're faults that are also showing up that are cross strike or cross the grain of the rock. So if we think the grain is just like this, but notice you have sort of these water gaps and that come across like this, almost perpendicular to the grain of the rocks. So those are geologic lineaments that can tell us a little bit about how these rocks have been further jointed, further deformed by brittle deformation rather than the metamorphic ductile deformation as they've aged over time. All right, so I want to start off with an example over here in northeastern Nelson County, right up here. So if you're looking where we are, we're on the eastern edge of Crawford's Knob. This is George Washington National Forest, and over here is 151 coming in, just a little section of it. And what I'm going to do is turn off this 2018 aerial photography and turn on the LIDAR. Now you can see there's a lot going on in this LIDAR now that we can look at it with a little bit more detail. Here I've circled some areas where we seem to have a lot of really high relief. This is the slope shade, by the way. And then we also have these areas where I would call them geologic lineaments, these straight line features that seem to be kind of, I can pick them out really easily from the LIDAR. There's a lot of other features, but let's just focus on those right now. All right, so this is the geologic map for this area. This is the Greenfield geologic map that was mapped by a geologist that used to work for us, Jerry Bartholomew, in 1977. And you can see there are a lot of different rock types just in this image. But again, what I want you to focus on first is the stuff that's in the ovals here. That is part of what's called the Swift Run Formation. Swift Run Formation is a metaconglomerate, so a conglomerate that has been metamorphosed, a rounded pebble rock unit that has then been metamorphosed over geologic time. And it's not a great outcropping rock. It doesn't show up on the surface very well. And I think what we're seeing over here on the LIDAR is evidence of why it doesn't show up very well. Because it's a metaconglomerate, it erodes away and it tends to form these cliffs right up next to this green unit, which is the Catoctin metabasalt over here, which tends to be in our area a high relief geologic unit. It builds really big mountains. Blue Ridge Mountains in this area are primarily composed at the top of a lot of Catoctin. So I think what you're seeing is this slowly eroding away Swift Run Formation as it abuts against the Catoctin Formation. Now, these little black lines down here parallel where Jerry had mapped a fault zone. This is actually now we know called the Rockfish Valley High Strain Zone, that fault zone that I picked out earlier. He mapped this in at the time as a fault. This is a pretty old map, a 43-year-old map, so we've learned a lot more about the geology since then. But I think what we're seeing in the LIDAR is that remnant of that fault zone. You're seeing, because it's right along the strike of where he mapped the fault. Now I tend to lose the fault as I go north. I kind of see something that goes up like that, but it's been buried underneath all of this material, which is alluvial material that has been moved by the river. So it's really been eroded, it's been covered, it's been buried over time. So you start to lose it. And the only way Jerry was able to map it was, see these little strike and dip symbols? That means that he actually collected data on rocks out there. So he was able to piece together where this fault zone was based upon the types of rocks that he was mapping out in the field. All right, so let's go to another example, maybe an easier example. Okay, so now we're out in the northwestern part of the county, and this is a really high resolution image, so it's really difficult for me to show you exactly where this is, but I've tried to put some road labels on this. Again, this is a 2018 aerial photograph. Can't see a lot of the geology with this one, but let's reveal the LIDAR here, and suddenly some really interesting features pop out. We have these high relief areas. These are, I would call them cliffs right here, and you have this other really high relief dark area here, another cliff. I see another set of hills here that seem to be almost a little disjointed. So when we pull up the geologic map, and this map was mapped, this is Big Level's geologic map, it was mapped by my agency in 2015. Now keep in mind, 2015, this is before LIDAR was available for Nelson County. We didn't get LIDAR for Nelson until about 2017, 2018. So this is map pre-LIDAR. Now let's compare what I've pointed out on the LIDAR to the geologic map. And I'm going to put some labels on so it's a little easier to read. So this maroon area right here is something called the Weaverton Formation, and that is a quartzite. Think of a sandstone primarily composed of quartz that has then been metamorphosed into a really hard rock. You hit it with your hammer, it bounces back and laughs at you. That's what the Weaverton is. Then you have another unit called the Harper's Formation, which is also composed of a lot of quartzite. So, and then you have another one called the Unicoi Formation, which is not quite as resistant, made up of lots of different metasediments, so shales, sandstones that are not quite as hard. And I think that's reflected really well in the LIDAR. So if you think of Weaverton being a very resistant unit, it creates these nice hills that are pretty sharply defined. And then again, we have the Weaverton cropping out down here. You can see that strip of Weaverton that was mapped right here, and it pretty much lines up with this exposure, this crinkly exposure of Weaverton down there. The Harper's, remember, is also fairly resistant, so it is also a ridge former, and we have the Harper's Formation forming a hill here. And what's interesting is I can see a continuation of it here, which definitely confirms this long feature in the geologic map, which is again a fault. So the Harper's Formation on this side and this side have been offset by this fault, which is really interesting, and you can sort of see that being expressed in the LIDAR, and pretty much the fault sort of follows this river valley in here. All right, so one last example. Let's go down to the central part, south central part of Nelson County, and we're looking in the Piney River area. So here is 56 coming in to 151. The town of Piney River is sort of in this area here, and again we have an aerial photograph. So let's strip that off and look at the LIDAR. Now, the LIDAR is a lot different in this area. And I'm going to draw a line in where I see a big difference in the rock type. So here we have a dashed line, and you can sort of see on the northwestern part, this is high relief area, very craggy, lots of mountains and ridges and valleys, and then boom, we go to the southeast, and it's fairly flat, rolling topography. Something has changed. And whenever I see something like this in LIDAR, I think there's got to be something geological happening. Well, there is. So if we pull in the geologic map for this area, this is the Piney River geologic map that was mapped by our scientists in 2008. And this this blue unit, this light blue unit, is a rock type called anorthosite. Anorthosite is an intrusive igneous rock that is composed of a lot of feldspar, like 90% feldspar, and that's what gives it the light color that you see over here. It's got so much feldspar in it. Now, the rocks that are in this dark blue area are essentially granitic rocks that have been metamorphosed. So they are composed of quartz and feldspar and biotite and a few other different types of minerals. But the anorthosite is a lot of feldspar. So I think what we're seeing here is we're seeing the difference in the way these two rock types erode over time. The granitic rock over here, because it has quartz in it and it has feldspar, it's eroding, those minerals are eroding at different rates. Quartz is slightly harder than feldspar. Feldspar is about a 6 on the Mohs hardness scale, whereas quartz is a 7. So that rock seems to be eroding differently, creating high relief areas over here. The anorthosite being almost 90% feldspar, it all seems to be eroding at about the same rate. So I think that's why we're seeing this difference in the LIDAR. So the anorthosite in this area is been historically mined for about the past 100 years. It's still being mined actually in this area. And if you've been looking at my slide kind of closely, you probably noticed that unusual feature right there that I've marked in red. So what is that? Well, that is the Boxley Material asphalt mine in Piney River. So this is currently being mined. They're mining the anorthosite. They're mining it to use for asphalt. The feldspar in the anorthosite is something that's useful for asphalt making. So that's what they're mining. Traditionally, they've also mined the feldspar for other uses. The anorthosite in particular has titanium in it from the mineral rutile. So they've extracted that for titanium dioxide, for pigments, and they've also taken it out for other reasons. But titanium mining and feldspar mining are the two big ones over here. So let's look at this on the LIDAR, and you can see just how disturbed this area has been by mining. Things that you really couldn't see if I go back over here. Notice this area over here, really hidden in the aerial photography, and it shows up like a sore thumb in the LIDAR with all that vegetation stripped away. So this is what an active mining site looks like. Human activity definitely puts an indelible mark on the surface of the earth. So this leads me right into talking about human activity in mining. So let's talk a little bit more about mining in Nelson County. So all of these blue dots, you can see these overlaying on the geology, those are mine sites. Those are mine sites that we have in our databases at DMME. Now, most of those, if not all of them, are historic mining sites. They are not active. They are not being mined anymore. As a matter of fact, the Boxley Materials plant is actually not in Nelson County. It's in Amherst. It's right off of the side here. And they are mining over here in Albemarle County, some soapstone at the Alberine soapstone quarry. So there is some mining that's going on, but really no active mining going on in Nelson County. But historically, there was a lot of mining going on in Nelson. So let's go back to Piney River over here and look at another mine site, a much smaller historic mine site, right in this area, right in the middle of the anorthosite. All right, so this is the Buffalo mine. This was mined for only a short amount of time in the late 50s, early 60s, but again, you can see that it left quite a mark on the landscape. We're looking at a much more zoomed in area of the county. You can see the remnants of the tailing pond and of the quarry, and they were mining something called aplite within the anorthosite. So this is what this would have looked like in the 60s. This is a picture of the mine from our files, actually. So it was a pretty active site. They were mining the aplite for ceramics to add in as an additive to ceramics. And you're saying, what is aplite? Well, aplite is another type of intrusive igneous rock. It's like a granite, except it's much finer grained. And in this case, the aplite is intruded within the rocks, within the anorthosite, as dikes. So you can see this lighter colored thing right there, that is an aplite dike, and that's what they were mining. They also mined, again, as I said in here, for titanium and for rutile and some of the other minerals that were useful for that. So let's look at another, let's move off from Piney River and look at another mine site. So here we are back at our map. So let's go over to this area of the county, in the eastern part of the county. This is, you can see all these mines sort of form a belt. This is the James River, Roanoke River Manganese District. So they're primarily mining manganese and iron in this area, in the late 1800s, early 1900s, primarily for steel making. So if we throw all those dots on top of the LIDAR, the dark blue dots, like these, those are manganese mines. The lighter colored blue, those are iron mines mined together. Now, laid over top of the LIDAR, you can really see that they tend to be mining right along this ridge right here. And that is not by accident. So let's overlay the geologic map on here. This is the Howardsville geologic map, mapped in 2015 by William and Mary students. And you can see almost all these little dots line up fairly well with this sort of yellowish geologic unit here. That is the Evening Group quartzite. And again, a quartzite is a sandstone, a clean sandstone composed mostly of quartz. And within the sandstone, along breaks and fractures, there's this material called manganese dioxide. It's black. It tends to form along those fractures. And as the quartzite erodes into soil, it gathers together, and you can actually mine it. Now, they don't mine it very much, well, they don't mine it at all anymore in this area, but historically there was mining happening here. So the Evening Group pretty much was providing those manganese deposits. Now let's take a slightly closer look, because we're zoomed out pretty far. So let's zoom in a little bit closer. Okay, can't see a lot here, but this is the 2018 aerophotography. So let's strip that off. All right. So here we see some very small mining features, and I want you to just take a minute and see if you can pick these things out. So we have someone I work with, our orphan land specialists. They look at orphan mine lands that have been mined historically but are not mined anymore, and we don't know where a lot of those are. So he has been going and trying to document them, and he's been using the LIDAR to try to locate these features much better. So now that I've given you a little bit of time, can you actually pick out what I'm looking at here? How about there, there, and there? Those little pits in the LIDAR, that's what we're looking for. Those are either mining prospects or they are tiny little quarries, mining pits, that were being excavated for manganese and iron at the turn of the century. And here's what they look like in real life. They just look like big pits that have been dug 30 feet into the ground. So my colleague would go out, and he would go out with a GPS unit and take information of these. They'd go into our databases that are available online, but the LIDAR really helps him get these in the right locations so that we have these documented properly. All right, let's go to a completely different area of the county. We're going back over into my favorite geologic unit, the Catoctin metabasalt. And what you're seeing is a portion of the Sharando geologic map from 1977. And all of this green is Catoctin, and there's a bunch of different types of Catoctin metabasalt. That's what the various greens mean, but let's just call it all Catoctin for right now. And let's look at this on the LIDAR. So there's a lot going on here. There's a lot of erosion going on, but let's zoom in a little bit further so we can see these mines right there. So again, here's the aerophotography. Let's strip that off. And now we're looking at these little pit features there. Those are adits, mine openings, for copper mining. They were mining copper in the late turn of the century, 1800s and 1900s in this area, for copper in the Catoctin. So the Catoctin, if you think about it, would get injected with hot fluids as it was being metamorphosed. So breaks and fractures in the rock, hot fluids get injected. You got to think about, these are buried thousands and thousands of feet deep. So these rocks really heat up and things move through them, groundwater and other things that have percolated in. And as those hot fluids move through the rocks, it's depositing different minerals like malachite and azurite, and in this case, native copper. So let's take a look at what one of these looks like. And from what I understand, some of you with the Wintergreen Foundation, with the symposium, have probably been on a hike to look at these, but just in case, this is what they look like. This is an adit, so this is an opening into a mine opening, And what's really interesting to me as a geologist is I can see the texture in this rock. So the darker grayish green over here, that is the catoctin formation. But you see these blobs, these blebs over here? Those are some other units that have gotten broken up and mixed up and included in as this unit has been deformed and those hot fluids have been injected. So as those hot fluids got injected, they deformed and cracked up and broke up those rocks into these blobs that then got even further deformed by metamorphic action. And then someone later on discovered that you could get copper out of these materials, and they went in and dug them in, and that's why they are there now. All right, so we're going to kind of take a hard right here, but we're still in the same vein of things, and we're going to go talk about how the rivers have really formed different features on the surface of the earth in this area. So let's go back to our geologic map. We know that the geology, some rocks are more resistant than others, and the water erodes those rocks in different ways. So let's just take off the geology and look at the LIDAR that is underneath. And I've put on major rivers, so we have Ty River right here that comes down, and it kind of goes off into Amherst County and back in, and then takes a hard right. We have the Rockfish here, and the James River, of course, on the eastern boundary of the county, and the Piney River on the western part of the county. Now, what's really interesting is instead of going with the grain of the rocks, the Ty and the Rockfish pretty much are going perpendicular to the grain of the rocks. And remember when I was talking about lineaments and fractures and joints within the rocks, they are basically using those weak areas and are the water is traveling down those. Now, once the water in the Ty gets down into our meta sediments here, you tend to form a more trellis drainage pattern, and you're following the actual grain of the geology in this area. So kind of interesting. Now I want to go and look at something a little more specific here along the Ty. So this is our aerial photography. To the north, that is going to be, if you were to continue north up 56, you would get to Tyro. If you were to continue south along 56, you would go to Massey's Mill. So we're somewhere in between. And here's the Ty River on the aerial photography. You can see flowing down like that. So for this just little section of the Ty, I created a DEM, a digital elevation model. And these light areas right here are the highest elevation. Then you have moderate browns, which are slightly lower, and then the lowest elevations are these light colored blues and greens down here. So the Ty River is going from an area that is higher elevation down to lower elevation. So that's really cool. We can start to see some features, some ghostly meanders coming out, but there's a technique that brings out those meanders a little bit better, and we convert the DEM into something that's called an REM, and that's a relative elevation model. And what that means, it shows the relative elevation of the river, in this case the Ty, compared to the elevation of the mountains on either side of it. So in the middle, you have the lower elevations, and on the sides, you have higher elevations. So it's almost like you're burning in the Ty River into the DEM, so you're able to see a lot more features within that river valley. That's really helpful for geologists who are mapping along floodplains and geologists who are mapping superficial geology, so we can see the course of the Ty River as it has flown over geologic time, or flowed over geologic time. So let's zoom in on a little bit of this. So here's a zoomed in section. What's really interesting to me as a geologist is you can very easily see these ghost-like channels right through here. The Ty River over time has moved back and forth across its floodplain. And what you're seeing are the former courses of the Ty River as it has moved across its floodplain. These are old meanders, essentially, old cutoffs, and now we have the current course over here. So this is helpful when you're doing floodplain mapping. We can tell where the low areas are and which areas are more likely to get flooded during a big storm event. Now, the other thing that I notice is over here. So I've kind of outlined what I'm seeing. I'm seeing this crinkly area. It looks like it has a little more texture than this area. It's a little smoother over here. This has a lot more texture. And I said, oh boy, I know exactly what that is. So I pulled up some aerial photography that I had and I overlaid it over this area. This is a 1969 aerial photograph that was taken right after Hurricane Camille. And sure enough, what we're looking at is flooding along the Ty River that was associated with the hurricane. So all of that craggly stuff is the material that was moved by that flooding. Chance. There's a reason why they did that, is because they were slightly lower. They were basically forming the equivalent of oxbow lakes that were temporary and that dried up. But that's why they did that. These are geomorphic features. All right, so let's go to the northeast, up this direction, up Cub Creek. All right, here we have the Cub Creek Valley. So Cub Creek goes up to the northeast like this. This is Cub Creek Road, which essentially parallels it on the other side of the valley. Cub Creek is a tributary. It doesn't have as much power as the Ty. It's not moving as much water. So we don't see a lot of those pretty meander features as we did along the Ty. But we do see some kind of interesting things, especially up here where it takes a hard bend to the right. So let's zoom in to that area. So here we have Cub Creek Road coming in. This is Carter Hill Road coming down, if you want to orient yourselves. And the first thing I notice is we're getting that more crinkly, craggly stuff right in here. Right there. And then right in here we're seeing some more what I would call flood material. But it was curious. I was wondering why we see just a patch right there. Because when I brought in the 1969 aerial photography, you could see this whole area was essentially inundated. The white areas are usually high reflectance materials like sand, and you can see that we have a lot of overwash that came through in this area, and nothing really looks the same over here. It's all been reworked. And what happened after the hurricane is that a lot of this then got repaired. Fields were cleared off. This area probably used for farming. So people wanted to clear off their fields, get all the rocks and cobbles and everything else out. And probably what happened, if we look at the modern photography, we see there's a stand of what I would guess is probably a tree farm. You can see all these trees are kind of in a row, so definitely not natural. And probably everything was cleared off, pushed off into a big pile. And that's why we're seeing those kind of pile of rocks in the field right here. And then they probably pushed most of the material off along Cub Creek to get it off of this agricultural field here. All right, but things start getting really interesting as you keep going up Cub Creek Road, up Cub Creek, up the hill, up the valley. This is again an REM that I created. And what I really want you to focus on in all of this is that feature right there. That's very strange. I looked at that and said, what could that possibly be? So let's take a look. All right. So what we're looking at is this feature right here. This almost looks like a bird's foot delta like you would see along the Mississippi River. And I'm going to outline what this is. So let's bring on the 1969 aerial photography. So here's Cub Creek flowing right through here. And what this is a landslide. This is the tail end, this is the toe of a landslide. And it has piled up all of its material right up against Cub Creek. This is the track of the landslide. It's a particular type of landslide called a debris flow. They're very dangerous. They travel very swiftly downslope using existing tributaries like first and second order drainages. And this one has ended up right slammed up against Cub Creek. Now this whole valley was full of debris flows, but this is a pretty easy one to see, so let's just take a look at this one. So here we have Cub Creek flowing this way at high flow, like during the hurricane when you had flood conditions. All of this unconsolidated material here that was from the debris flow, think cobbles, boulders, soil, things like that, were being reworked right away as they moved down from the mountains down into the valley. And you can see that. You can see the reworking of these materials in this sort of direction from the flow of the water. And then as it got pushed, all this material got pushed, it actually formed this big bulb of material down here too. So the Ty at flood stage was really rocking, the Cub Creek at flood stage was really rocking and was moving all of this material from this debris flow. So here we are, just take another look at this. Let's zoom way out, okay? And this is leading me to talk about my next topic of landslides, which is near and dear to my heart and my specialty. So let's zoom out here. All right, again, 1969 aerial photography. You can see just how long this feature was. We're looking at several thousand feet. This is a pretty major debris flow. There's also something coming in over here into Cub Creek. So let's talk about, I keep using these terms. Let's talk a little bit about that. Let's look at the LIDAR first. You can see kind of that craggly area here, all of this that's been incised by the debris flow. And this whole area is just full of landslide debris. So the aerial photography is really handy. It's really useful, that particularly the post-hurricane aerial photography is really helpful for me as a geologist in locating where these features are. Because by 2018, it's nearly invisible. You can't see a thing. But the 1969 photography clearly shows, this is an area of Davis Creek, these little debris flows that are leading into this more major debris flow here. If I strip off the 2018, it becomes a little more obvious where they are. You can see a nice headscarp here that was cut in, and you can sort of see something right there. So let's talk about landslides. Let's talk about, I keep using all these terms, debris flow, things like that. Let's talk about what they are. Of the different types of landslides in the Southern Appalachians, these three that you see right here are probably the most common. Debris flows, debris slides, and rock slides. Debris just talks about the size and the makeup of the material that is moved by the landslide, and whether I'm talking about a flow or a slide, that has to do with how the material is physically moving downslope, whether it is flowing like a river or whether it is sliding along a surface. So let's take a look at these individually real quick. A debris flow is definitely the most dangerous type of landslide that we get in the Southern Appalachians. They tend to have a very obvious scar. We were seeing some of that earlier. They tend to follow narrow drainages, first and second order drainages, and tend to have a deposit of material down to the bottom along a toe. They tend to occur on slopes that are composed of thin soils over bedrock, which we definitely have in Nelson County. And a lot of the landslides from Hurricane Camille were this type. They were these long, narrow debris flows, just like this one here. And I like to call them, or think of them as, basically a flood on steroids. So imagine you have this wall of mud and rock and trees that flows. Think about the consistency of concrete, but it flows downhill. And that all has to do with how the momentum and the water, the sheer amount of water that is in that material as it moves downslope. And this is exactly what happened during Hurricane Camille, especially in the Davis Creek area near the center of the county, just to the west and north of Livingston. All of these features that you see coming down off of the mountains here, those are debris flows. This is the Fortunes Cove area of Nelson County, again to the west of Livingston. It's also a nature conservancy site. If you want to go and take a hike out here, I highly recommend it because you can see all these features from Hurricane Camille. Let's go take a look at this section of Fortunes Cove up here in the mountain. And you can still see many of the features from Hurricane Camille in these landslides today. If you were to go and hike out there today, preferably in the winter, vegetation is off of the trees, you could see things like headscarps where you have the exposed bedrock. That's that scar that I was talking about earlier. They tend to have long, narrow tracks that have been incised. You could see these. And then there's a lot of debris, big bouldery debris. Those boulders didn't get there by accident. They were moved. They were moved by water and soil by those landslides. So debris slides. Debris slides are kind of like a debris flow, except they tend to be wider than they are long. So think of them, where debris flows are long and narrow, debris slides tend to be short and stocky. They don't tend to travel as far, but they tend to be a lot wider. Probably the most famous debris slide, if you're familiar with this one, is the Oso landslide in Washington State in 2014. This scale is quite large. It's an immense landslide, and it ended up killing several people, a lot of people. So they can be very dangerous at these sort of scales. Most of the debris slides I see are much smaller. They're not nearly as big. This is the debris slide from King William County in Virginia, which is in the coastal plain. Actually, it's one I was called out as an emergency response for this one. These two houses ended up being condemned, partially because for this house over here, it was affecting the structure of their foundation. So the landslide was actually cutting up into their foundation. But for this house over here, they lost their septic system. This is the septic box for this house. So you can't really live in a house if it's got a ruined septic system. But in these photos, you can sort of see the general setup of a debris slide. Here, kind of wider than it is long. You have some back rotated trees over here. And then at the bottom, this is a beautiful roll front tow where all of that material has basically moved over top of the original ground material as it has moved down slope. So I'm doing a lot of this landslide mapping that I've been talking about as part of a project that I'm currently working on in western Nelson and Albemarle counties. This is a FEMA funded pre-disaster mitigation grant project. We started it in 2008 and we're anticipating we will be done in March of 2021. So we are doing landslide hazard maps for western Nelson County and western Albemarle, but we're going to be focusing today on western Nelson County. And basically the project is completed in 4 different phases. The first phase being the part that we're talking about today, using LIDAR to identify modern and historic landslides. We've also completed the second phase, is the geologic field mapping of those landslide prone areas. So this winter, before the pandemic hit, we were out there mapping a lot of these landslide features in the field, collecting soil information, collecting geologic information. And now we are taking all that information and we're going to be doing susceptibility mapping, which I'm starting to do pretty much in the next month. And then after all of that is done, we'll present those data products and the results to the emergency management community, to Wintergreen, if folks would like to have me come up and talk about that, and also at public meetings. So we use the LIDAR exclusively in the first phase of this project to identify headscarp locations, landslide tracks, as well as ancient landslide deposits. And let me show you a few examples of those. So here we have the aerial photography for Nelson, and can't see a whole heck of a lot here, but let's strip that off and look at the LIDAR. And suddenly things come into focus. We can see much more of what is underneath the aerial photography. Now keep in mind, before LIDAR, we had to use aerial photography all the time to identify landslides. So this is a huge improvement. So let's take a look at these features. So at the top we have these different headscarps, right there, right there, right there. A long, narrow debris flow track, as you can tell, has been very incised compared to its surrounding material. And on this one, this has some coalescing debris slides. Remember, those are the short and stocky ones coming into the main debris flow track. That's not unusual in Nelson. We see that a lot. Over here on the right, we have, this is the debris flow track in a different area. This one is in Davis Creek. And I don't know if you noticed, but this is a little road, probably an old farming road. It's invisible on the aerial photography. But on the LIDAR, you can't hide from that. It's real. And these little debris slides have essentially destroyed this road. So these little things, they're not very big, 75 feet across. This one's probably 50 feet across or so. And those are actually combining with the major debris flow that then went down into the valley of Davis Creek. So we also use the LIDAR to outline the debris flow tracks, landslide tracks, and that's what all this pink stuff is that you see in those slides. So we basically draw polygons. So the green dots there are landslide headscarps, and these outlined areas are the tracks of debris flows. Over on the right, this is Fortune's Cove. I was talking about that earlier. If you want to go on a hike, again, that yellow line, those are the trails that lead up into the cove itself. And immediately, after about 5 minutes of walking, you're starting to walk over landslides associated with Hurricane Camille. It's really extraordinary if you're a dorky geologist like me. So all of this pink stuff has been disturbed by Hurricane Camille landslides. So many, many coalescing debris flows in the Fortune's Cove area. We also see some kind of unusual features if we really dig into the LIDAR. Again, the green dots at the top are headscarps. This is the track coming down. And right here, you really can see the toe of all of that debris flow material that has gathered into the valley here. You can also see individual boulders. As we were doing our geologic mapping, we would go out and try to verify what we were seeing on the LIDAR. And it was spot on. We found that these big chunks, they're not just artifacts in the LIDAR, they are real. These are boulders. And those boulders are from Hurricane Camille. And all of this material, this Camille landslide deposit, is over top of an ancient landslide deposit. So these ancient accumulations of landslide material over geologic time. So these ancient deposits are everywhere, essentially, in mountainous areas, particularly the Southern Appalachians. This pumpkin-colored stuff is what I'm calling a landslide deposit. And this is what it looks like in real life. Imagine an accumulation of bouldery material that looks like it's just eroding away, like ice cubes in a glass. Over time, you have these big bunches of boulders to cobble-sized material. If we were to take an exposure of this is along a road cut, you can see that it's primarily unconsolidated material. It's not bedrock, it's not just nice sandy soil, it's boulders, cobbles, things about the size of my fist or larger that are eroding away into this sort of reddish mixture of material. So these are accumulations of several landslides, lots of landslides. Generally these things are thousands of years old, but they are accumulations of unconsolidated material. So when you're making steep cuts into these, you have to be careful that you're not making them too steep, because they can collapse and they can cause modern landslides, but they are really good for holding groundwater. So a lot of people will put their wells into these because they are easy. It's much easier to get through this material than it is to get through solid bedrock. So we map these because we consider them to be a moderate hazard for landslide susceptibility, because if you could see this river deposit here, if you're going to have a modern landslide, it's most likely going to travel down here in places where landslides have traveled before. So that's why we put these on the map. So let's take a look at one of these fans from Nelson, and you could start to see really interesting features on it. The upper part of the debris deposit tends to be very craggly. A lot of this is materials being sourced up here from this outcrop. This outcropping of geologic material, and then it's accumulating downslope. So the lower fan surfaces tend to be very smooth. You can definitely see a color difference between this part of the topography and the fan surface, and that all has to do, in this case, this is a slope shade, with these lower slopes, and these are steeper slopes over here. You can also see individual lobes, so these lobes of material that have basically collected as the material has moved downhill over time. So we're probably looking at several generations of landslides that have formed these debris deposit features. The other reason that we map landslide deposits is because they tend to show where landslides may occur again. And it's really easy to see examples of these in Nelson County. So here we have a nice debris fan, a nice landslide deposit that has been collecting over geologic time. But on either side of it, there is essentially a first order stream, a young stream, and those are full of Camille landslide materials. These are the tail ends of debris flows that occurred during Hurricane Camille. And we see this setup a lot, where you have a debris flow and then or a debris fan, and on either side of it, where you have drainages that have developed, new modern landslides tend to take advantage of those and will travel down those drainages, just like we see here during Hurricane Camille. So again, that's why we tend to consider these to be a moderate hazard. These areas on the side I would consider to be a high hazard for landslides to occur in the future. So that's why we map them. Some other features, and these are brand new, that we've been identifying in Nelson County are what I like to call weathered landslides and relic landslides. So here we have again our wonderful aerial photography that pretty much shows nothing. But I do notice this sort of lump coming in. This is the tie again. And I noticed that this was offset a little bit in the aerial photography. So let's look at the LIDAR here. Well, that offset was caused by a landslide of some sort, and it looks like it's multiple generations of landslides. You could sort of see this almost stepped appearance as it's been eroded away by the tie. But what I don't see on this one is a really good headscarp. This is probably cliff. This is cliff over here, so outcropping rock. But I don't see a really nice ice cream scoop looking headscarp at the top. And then we started seeing these really weird things. We called them the mashed potato deposits. We weren't sure what these were. So this was a major focus of the work that we did over the winter of 2019 into 2020 to figure out what these are. And this is what we've decided to call them: weathered landslides and relic landslides. So weathered landslides seem to be the remnants of a single landslide event, but we can't actually correlate them with any known storm event. So I can't correlate them with 1969. I can't correlate them with 1995 or any modern storm. I can't locate them on the aerial photography. But what we do see is that they are there. They tend to have some evidence of a weathered headscarp. They have a narrow appearance. The lateral boundaries of them tend to be weathered. But they do sort of look like a modern landslide. I just don't know how old they are. They tend to have a hummocky appearance in the main body of the slide, and you can definitely see this one here. This is right outside the gate for wintergreen. And the other thing that we have noticed is they tend to be found in areas that are underlined by our old friend, the Catoctin metabasalt, which is really interesting. Now, relic landslides seem to be several generations of various types of downslope movement, whether that's regular old debris flows, rock falls, other things like that, slumping. All evidence of scarping, headscarps, tend to have been weathered away. And they just leave this hummocky, mashed potato-y looking thing on the slope. We've noticed that they tend to occur below a cliff face or below an outcrop source. In this case, it's happening, or this relic landslide is occurring below Catoctin outcrop. And as you can see, it's not long and narrow like that previous one. It's just this lump of really strange material on the side of the mountain here. And this is below the ski slopes. So the ski slopes would be up in this area if I kept on going for wintergreen. The other thing we notice is these relic landslides tend to generate modern landslides. So if we assume that all this relic landslide material is unconsolidated material, it's really easy to get water moving through those and to form modern landslides which are initiating from them. Again, these tend to be only found in areas underlain by the catoctin. Very strange. My primary concern is that these may be a problem for construction and they may initiate new landslides. So these are definitely going on our final maps because we think that they're very important to point out. So let's look at an example of this. Remember I said that they're mainly associated with the catoctin. So what I've done is I've taken the catoctin and I've just highlighted it. So it's in green because it is our friendly green geologic unit, metabasalt. And let's take all of those relic landslides and overlay them. That's what these orange and pink things are. And you can see it's a really good correlation. It's very strange. Now, they mainly tend to be found in what we call the western limb of the catoctin, not in the eastern limb. I haven't seen any out here yet, and I think that primarily has to do with the relief. We just don't have the relief here as we do out here. So let's zoom in a little bit, look at these a little bit better, and you can see most of these, all these pumpkin colored things are the relic landslides. The pink are the weathered landslides, and I differentiated them based on relative age, essentially. They're either forming within the catoctin or they are being generated from the catoctin. So they're moving downslope outside of the boundary of the catoctin, but being generated, materials being generated from it. Very strange. So let's zoom in again in this area. So this is the Stony Creek area of Wintergreen. You can see all of the roads leading up through the development. And the first thing when I looked at the LIDAR, this is Crawford's Knob up here, composed entirely of catoctin, is those mashed potatoes on the side of the hill. So let's look at what we currently have in the database here. All these are outlining what I'm calling these relic landslides. So there's a lot of them here. We think this is important for the landowners to know about. So let's take a look at what these look like on in the real world and with boots on the ground. They're really subtle. It's not very obvious, and unless you were trained to be able to look for these features, I don't think most people would be able to notice them. We certainly didn't know they existed until we had the LIDAR and knew what to then go out and look for. So when you're out here and in the middle of these features, you tend to see basically hummocky lobes with cobbles and boulders. Over here, that's what these kind of look like. So just these accumulations of kind of bouldery colluvial material, nothing too unusual. And you also have boulder streams. So these are long linear features that are composed of boulders, usually 1 to 2 feet in diameter, and they tend to be long and linear, and any sort of matrix within them, fine grained material, has been washed out. Not unusual. We see this a lot in the Southern Appalachians, see this a lot in Nelson County. And we also tend to see these kind of shelves of material. So you'll have a higher area, and then as you're walking down, you'll drop down about 8 to 10 feet and you're down into another shelf. And I think what we're looking at is several generations of rock falls that have accumulated in this area. Now, I've marked the houses that are within this. This is the child's property. This person had structural damage to their foundation, and I think it's because they were within this relic landslide. And then we also have 2 other houses. Now, there's not saying that you can't build in these areas. I just think you need to be more careful. It's going to be really important for these homeowners to make sure that the drainage in particular is kept away from the house. So you don't want any water to be accumulating in this material. We want it to whisk it away from the house, because once you get too much water, as we know, water tends to generate landslides. We don't want the water accumulating and then having any sort of failure within the material itself. So as long as these landowners are aware that they are within these and that they are looking at their drainage, they're looking at where their storm water is going, I think they'll be fine, but I think this is something that people just need to be aware of and to keep on top of with their regular home maintenance. So I want to wrap everything up with back in wintergreen, and I'm going to try to bring together everything that we've learned so far in this presentation with geology and superficial geology and hazards geology, and just bring all of it together. So this is the gatehouse for Wintergreen Drive, coming back up, winding its way up to the top. These dashed areas are trails within Wintergreen. Many of you have probably hiked on them. If you were with me last year at the symposium, you hiked on them too. So let's overlay the geology here. This is the 1977 geologic map that Jerry Bartholomew did for this area. And I put the labels on for these different formations. Again, our favorite green formation, the Catoctin up here. We have a band of Swift Run, that's that metaconglomerate coming down. And then this orange unit over here is the Peddler Formation. That is essentially, it's called a charnockite, but think of it as a granitic rock, essentially. And then you have how he marked it as a fault coming down the valley here. And this yellow stuff is alluvial material that has been moved by river action. So we have the basics of the geology that Jerry did, and this is pretty good. So let's look at this on the LIDAR. I'll leave the labels on, but this is where the rubber really hits the road with the LIDAR, and you start to see all of these fascinating features starting to come out. So those are our weathered and relic landslides on the side here, and this is where we recommend that you have to be careful if you want to build. So far nothing has really been built over here, but it's good to be aware of where these features are. Again, right below the Catoctin Formation, the Swift Run is probably hidden somewhere underneath of here. Over here with these orange deposits are more traditional colluvial material that's long and linear, that has infilled these valleys. So all of this material is being eroded from upslope from the Catoctin. And then what I do is I then take all of that and I digitize the polygons for all these different features on top, and this is what so far I've come up with. So we're able to add a lot more detail using the LIDAR, detail that we could have never seen before without it. And I think this is really going to improve the mapping for this area. It's going to inform the public, it's going to inform people of the geologic hazards that they should be aware of when they're doing any sort of building, road building, construction, anything like that. So we're hoping that's what these maps are going to be used for in the future. So that's it, guys. That's what I have to say. I hope you found this interesting. If you have any questions, you can always email me at my email address. If you want to know more about LIDAR, please visit our website. We have a whole page devoted just to LIDAR with even more examples, information about where to get LIDAR, how to download LIDAR, things like that. So please take a look at our website and let me know if you have any questions. Thanks.